All right, welcome to this explainer. Let's just dive straight into the explosive growth of artificial intelligence and honestly, the brand new challenges it's bringing to the table. For the longest time, we really thought of AI as this single massive brain. But as we scale up to solve massive real-world problems, like managing complex power grids or coordinating fleets of autonomous vehicles, that single brain approach, it just bottlenecks. So the solution here isn't just building a smarter AI, it's a completely different architectural approach altogether.
To put this into perspective, just in the first quarter of 2024 alone, multi-agent systems pulled in a staggering $12.2 billion in funding. $12.2 billion! And that's spread across more than 1,000 different transactions. So this clearly isn't just some niche research topic anymore. This is the next massive leap in tech. Major industries, from healthcare to mobility to defense, they are all going all in on this. They're betting on a future that's powered not by one single AI, but literally thousands of them working together seamlessly.
But of course, this raises a really crucial, highly complex question. When you have millions of AI agents running our infrastructure all at the exact same time, who is actually the boss? Seriously, if you've got countless autonomous programs managing our energy, our logistics, our data, how do you stop it from turning into absolute chaos? How do these individual agents know what to do, who to report to, and how to resolve conflicts, especially when a human can't sit there micromanaging every single millisecond?
Well, today we're mapping out the blueprint of swarm intelligence. We'll be looking at meet the multi-agent system, structuring the AI hierarchy, nature-inspired AI optimization, powering the smart grid, and finally, humans in the loop.
Okay, let's jump right into Section 1. Meet the multi-agent system, from one brain to thousands.
So, to prevent that total chaos we just talked about, engineers organize these programs into what are called hierarchical multi-agent systems, or HMAS for short. Think of it kind of like setting up an automated chain of command. Actually, it's very much like a human corporate structure. Instead of a flat organization where millions of agents are just yelling over each other trying to communicate all at once, HMAS delegates the decision-making. You've got higher-level agents actively overseeing the lower-level ones. This layered setup allows the system to flexibly adapt to whatever the task demands, making it entirely possible to manage intense complexity on a really massive scale.
Which brings us smoothly to Section 2, structuring the AI hierarchy, essentially building the organizational chart. Independent researcher David J. Moore actually breaks this down beautifully into a 5-axis taxonomy. And the goal here isn't to find one single perfect design, but rather to weigh the trade-offs. You have to ask things like, how is authority distributed? Does the information flow top-down, or is it bottom-up? Are the communication networks static, or are they dynamic? Really understanding these specific variables gives system architects a direct lens to compare different coordination designs based entirely on the specific problem they're trying to solve. Just look at the control axis, for example. Compare a strict, centralized factory foreman approach to a decentralized flock of birds where there's no single leader calling the shots. In a centralized system, you have that single brain computing tasks and barking orders. It's super efficient for global optimization, sure, but if that central leader fails, the whole system goes down. On the flip side, a fully decentralized system has no single boss. It's incredibly robust to failures, but as the group gets larger, it really struggles to achieve one coherent global goal. And that is exactly why recent research is leaning so heavily into a hybrid approach, basically marrying the scalability and oversight of a hierarchy with the resilience of a decentralized swarm.
All right, let's move on to Section 3, Nature-Inspired AI Optimization, looking at the mind of the machine. Computer scientists are turning to swarm intelligence, literally drawing direct inspiration from biology to coordinate these abstract software agents. Because when you think about it, nature has already spent millions of years doing the R&D, perfecting how massive groups of simple organisms can solve incredibly complex logistical problems without a central manager. By mimicking these biological phenomena, engineers can build algorithms that offer incredibly effective solutions to large-scale, nonlinear optimization problems. Take the gray wolf optimization algorithm, for instance. It mimics a literal wolf pack hunting prey in the wild. You have the alpha, who provides the best solution and directs the hunt. Then the betas act as subordinate advisors, while the deltas scout and the omegas basically surround the target and follow the pack. This biological hierarchy results in some phenomenal, incredibly rapid optimization. Because the system has this structured chain of command baked right into the math, it converges early and makes extremely robust decisions.
Similarly, we have ant colony optimization algorithms. These use digital pheromones to help autonomous agents collaboratively find the absolute best paths. Just like real ants leave chemical trails guiding the colony to a food source, these digital agents leave mathematical markers behind. As more agents find a successful route, the concentration of that digital pheromone increases, which reinforces that path as the optimal one. It is incredibly efficient for clustering data and routing. Now, it can sometimes be a bit time-consuming, and there's a risk of getting trapped in a local optimum, but it remains an absolute powerhouse in the Swarm toolkit.
So how does this affect you? Let's look at Section 4, Powering the Smart Grid, putting AI in the real world.
We all know that adding solar and battery storage to our microgrids is fantastic for the environment, right? But what's less talked about is that it creates massive power quality issues. We're talking voltage sags, swells, and severe harmonic distortions that can actually trigger blackouts. Because renewable energy is inherently intermittent, and because plugging it into the grid requires really complex power electronic converters, our electrical grids suffer from these deviations in magnitude and frequency. If these disturbances accumulate and get severe enough, microgrids literally have to disconnect themselves from the main utility grid just to protect the physical infrastructure.
To fix this, engineers use an AI-tuned Unified Power Quality Conditioner, and it operates in rapid-fire steps. First, it detects a sag or harmonic disturbance in the grid. Next, the AI agents instantly calculate the optimal mathematical compensatory voltage or current. And finally, the system injects that exact correction to instantly stabilize the power flow. Traditional conditioners are slow and rigid, but by using these AI swarm algorithms, they become highly adaptive. The AI neutralizes the distortion the millisecond it hits.
The results are genuinely mind-blowing. Check this out. From the source material, by using the gray wolf hierarchy, agents successfully dropped dangerous total harmonic distortion from over 27% down to under 2%. It literally restored the power back to a nearly pure wave. This proves that using hierarchical, nature-inspired AI isn't just some fun theoretical thought experiment. It is a highly practical, robust solution for stabilizing the very energy grids that power our homes.
And that brings us to our final section, Section 5, Humans in the Loop, Managing the Swarm.
In high-stakes fields, think oil drilling or emergency management, human supervisors sit at the very top of the organizational chart. We delegate the high-speed tactical execution to the machines, but we retain ultimate authority over the critical interventions. We essentially become the strategic agents. The machines are handling those millisecond by millisecond adjustments that human reflexes just literally cannot keep up with. But for this dynamic to actually work, the system has to provide explainable upward reporting. The agents have to be able to tell the human operator exactly why a decision was made. That's absolutely crucial for fostering the trust needed for humans to confidently delegate these tasks.
This perfectly illustrates what we call a temporal hierarchy. In a complex operation, lower-level rig agents act continuously on a very short horizon, reacting in mere milliseconds. Sitting right above them, area coordinator agents might look at a time frame of minutes to route power and prevent cascading failures. And sitting at the very top of all that is the human manager, planning the big picture strategy over days or weeks. By separating decisions across these different timescales, the human isn't overwhelmed by a flood of data, and the agents aren't bogged down trying to compute long-term strategy.
As we rapidly move toward integrating conversational large language models to manage these incredibly complex swarms, I want to leave you with this final, vital thought. If an LLM becomes the alpha agent of our power grid, how do we ensure it truly shares human values? We're looking at a near future where we might just speak a natural language command to an LLM, and it perfectly translates our intent down to a massive hierarchy of tactical machine agents. But as our source text strongly warns, integrating these stochastic, learning-based agents into safety-critical infrastructure has to be done with extreme caution. We absolutely have to ensure that the very top of our agent hierarchy remains permanently aligned with human intent, human safety, and human values. Thanks so much for joining me for this explainer. Keep asking questions and definitely keep exploring these incredible systems being built all around us.